Hey everyone, today we are going to be talking a little bit about factor analysis and principal components analysis with a focus mostly on factor analysis. This week we're going to be exploring factor analysis using SPSS. We will use SPSS in class to do both exploratory and confirmatory factor analysis, and we're going to talk a little bit about each of those. Today, we're just going to have a kind of a brief overview of what we will be talking about in class. So let's kick this off. So, different types of factor analysis. We have both exploratory and confirmatory, and we'll talk about what that means here in a little bit. And then we also have principal components analysis and factor analysis. And they differ a little bit, mostly in terms of how you think about the theory behind your data and the theory behind the responses of the items that you've got. But before we get to that, we need to talk a little bit about what a factor is. So for those of you who are in psychology, you'll be familiar with the idea of kind of traits or latent factors. The basic assumption behind factor analysis is that there is some sort of underlying hidden trait, factor, or component, excuse me, that drives the way that we respond to certain items. This is going to be particularly important when we come to structural equation modeling, because you will see these latent factors made as circles with arrows pointing to items. And I want to make this point clear. The items don't drive the factor. The arrows don't ever go this way. Well, okay, so there are instances when the arrows go this way, but for the most part, what we're talking about with factor analysis is factors driving our score on a set of items, and then using the correlations among those items to identify our level of trait, or our basic score, our factor score on that given factor. And so when you think about factors, we often think about things like impulsivity, or negative affect, or positive affect, or emotion regulation skills. And so we have a bunch of different items that are used to rate or rank our location on a given factor. So let's start by talking a little bit about problems in factor analysis. First and foremost, unlike every other type of statistical analysis, there is no readily available criteria that we can gauge our results against. So, for example, in regression, right, we have a dependent variable, and we can predict variance or explain variance in that dependent variable. So we have an R squared. We have some sort of scale with which to understand the relationship between an independent and a dependent variable. Similarly, if we're doing logistic regression or profile analysis or an analysis of variance or anything, we have group membership, and how well we can predict group membership, or how well we can discriminate across groups. We don't have that in factor analysis. The next big problem is that after extraction, there is really an infinite number of different types of ways to rotate the data to find certain types of factors, and they all account for the same amount of variance in the original data, but with slightly different assessments of interpretability and basic kind of utility for the study or for science. So consequently, when we have an infinite number of mathematically identical solutions, obviously people are bound to differ regarding which is best. And you'll see a lot of arguments in the literature about people saying, no, I think a two-factor solution is best, or I think a three-factor solution is best. If you use an oblique rotation, or this type of rotation, or that type of rotation, you find something different. And then trying to provide scientific rationale for which type of extraction of factors, the number of factors that is most acceptable. One of the recent things I've been working on is primary and secondary psychopathy, and now there is a new idea that primary and secondary psychopathy are actually composed of 3 different types of traits that don't map on nicely to primary and secondary. And then some of the issues is that there's high correlations among some of these factors. And so it's a constant struggle to find the appropriate assessment for the underlying traits, especially since, as we said at the beginning, these traits are hidden, right? They're not known. We're doing our best to come up with them. And this gets at kind of some of the problems with exploratory versus confirmatory, but we'll get to that later on. The last major problem in factor analysis is that it often has been used to salvage poorly conceived research ideas. When no other kind of statistical procedure is working or applicable, people will often say like, oh, well, let's do a factor analysis of the data. This is a terrible idea. It's a way to try and find order in what would otherwise be chaos. And again, with multiple types of rotations, which that probably doesn't make a ton of sense just yet, but with multiple types of rotations, you can find multiple different types of factor structures. The best case scenario here is trying to identify latent structures or latent factors and building your study in ways to try and address or answer questions linked to the specific number of factors. When we get to class, we're going to talk a little bit about exploratory versus confirmatory and how you decide if you should have 1 factor, 2 factors, 10 factors. There are a couple of different ways to do this. We're going to start out this week by looking at what's called eigenvalues and scree plots. Next week, we're going to shift to structural equation modeling, where we're actually able to compare factor structures based on model comparison tests. So let's talk a little bit about some definitions before we get too far here. The first definition that we have to cover is the observed correlation matrix. So the observed correlation matrix is the correlation matrix produced by all of your observed variables. It is just a simple correlation matrix. If you have 15 items and you correlate all 15 items, that's your observed correlation matrix. The reproduced correlation matrix, in contrast, is the correlation matrix that is implied by the factor solution that you come up with. The residual correlation matrix is the difference between the observed and the reproduced. It's just like it sounds, and it's very similar to what we would think of when we think about regression analysis and regression models. Your residual correlation matrix, ideally, you want to have very small residuals within that. In a good factor analysis, correlations in the residual matrix are small, which suggests a close fit between your observed and your reproduced matrices. Rotation. So I've said rotation a couple of different times, and we're going to talk a little bit about it here and a lot more about it in a few minutes. But we have 2 different types of rotation. We have orthogonal rotation and we have oblique rotation. Orthogonal rotation assumes that your factors are not related, that they fall on some sort of plane, 90-degree angle, and that this factor does not matter towards this factor. And I'm aware that me moving this mouse around is probably not the best way to describe this. I've got an image later on here in the video that you'll be able to see a little bit better what I'm talking about. In contrast, oblique suggests that there is no 90-degree separation between factors, and in fact, factors can be related. This is actually more common in nature. Oftentimes, factors are related. If you think about our most common model of impulsivity is what we call I like to think of the dual process model, where we have effortful control and impulsivity. But we also have this model called the UPS-P, where we have 5 separate factors, which include like positive urgency, negative urgency, conscientiousness, perseverance, and sensation seeking. And all of those are basically correlated. And so the idea with oblique rotation is that we allow for a rotation of all of our factors such that they can be correlated in some basic way. All right. Principal components versus factor analysis. So this is going to be one of the most important decisions that you'll make. Mathematically, the difference involves the contents of the diagonal of your correlation matrix. In principal components analysis, you have a diagonal that is composed of ones. And when you think of your basic correlation model, your basic correlation analysis, or a correlation table, oftentimes like the diagonal in your correlation table is listed as 1. You see it listed as 1 in papers and so on and so forth. Principal components assume that we have all of the variance is being used. In contrast, factor analysis assumes that only shared variance is being used. So if we look here, we have two items. We'll call these items, and each one is composed of a variance of 1, right? 100% of the variance is right here for this one, and 100% right here for the blue one. And then we have some shared variance in the middle. Principal components analysis would say that we are going to analyze all of the variance, and that means that we're going to analyze what we would have as far as shared variance here, but also this independent variance, which can be comprised of actual independent variance, and it can be comprised of error variance. In contrast, factor analysis would say, no, we're only going to look at the shared variance. And so in factor analysis, in our correlation matrix, along the diagonal, we would not have ones. We would have 0.3, 0.5, 0.6, et cetera, et cetera, et cetera. We have just the shared variance between between one variable and all other variables within that factor, or within the entire data set, depending on whether or not you are using a rotation or a non-rotation, or I mean an orthogonal or an oblique. And then we have factors. So let's talk a little bit about factors. If we are doing an exploratory factor analysis, this means that we don't know how many factors we have. We're taking a guess. Oftentimes, we will use a couple of different models to understand what's going on. The most common is to look at eigenvalues. We will look at the research, or not necessarily the research, but some of the earliest research, I guess, and recommendations for factor analysis have suggested that we use the eigenvalue of 1. And in principal components, an eigenvalue of 1 makes perfect sense because that is a 100% variance of one item, so it completely explains it. And anything below that means that you're no longer able to explain a single item, and consequently, you stop at that number of components. But one of the questions is, what happens if you have an eigenvalue? What's the difference between an eigenvalue of 1.01 and an eigenvalue of 0.999? It's almost nothing, right? And certainly if we have confidence bands around whether or not that's a statistically significant amount of variance, then it makes no sense. The other way that we've done this is by using something called the knee of the scree. And so you're going to see a scree plot in class this week, and we will talk about using that as an identifier for a potential spot to signal a cutoff for your number of factors that you think are involved. Now, ideally, whether it's confirmatory or exploratory, ideally you have some sort of underlying theory to suggest that you should have X number of factors, whatever that is. That doesn't mean that you have to settle on those. Oftentimes we will say that we believe that there's 3 factors, but the factor analysis, exploratory factor analysis actually indicated 4 factors. And we'll talk about ways to test a 3-factor versus a 4-factor model next week. Prior to structural equation modeling, you made a scientific argument for why it should be 3 factors versus 4 factors and so on. But more recently, with the advent of structural equation modeling, we've been able to test those models against each other. All right, let's talk a little bit about some other things that we need to be concerned about when we're thinking about factors. The first is sample size. And to to a smaller extent, or to a, not necessarily a smaller extent, but missing data that goes with sample size, right? So if you have very distinct factors and it's very easy to discriminate amongst them, smaller sample size is usually adequate. In fact, if you have very high factor loadings and very orthogonal factors, people can probably get away with sample sizes close to 100. However, if your factor loadings are much, much lower, or the squared multiple correlations are not at least in the range of roughly 0.5, then you might need 300 upwards of 500, and it's not uncommon to find samples of over 1,000 in order to have what we would consider an adequate sample size. Having gone through last week's class, we should all be capable now of conducting a power analysis for a confirmatory factor analysis, and determining, based on the factor loadings that you have observed in the literature or that you believe that you should have, what sample size is required to have adequate power for a given factor structure. If you don't have those things, you can always collect your data, examine your factor structure, and then run a simulation to determine what your power was based on the observed effects that you have in your model. So we've got that going for us now. Normality. So as long as principal components analysis and factor analysis are used descriptively as convenient ways to summarize relationships in a large set of variables, assumptions regarding the distributions of variables are not necessary, and certainly not in the same way that we like to think of for regression analysis. And again, if you recall from regression analysis, we were not concerned so much with the distribution or the normal distribution of our data, but with the normal distribution of our residuals. And that had more to do with the ordinary least squares approach that we were using to describe a model. And the same thing doesn't apply here. We do, however, assume multivariate normality if we're trying to determine the number of factors. And we'll talk a bit more about that in class. There are a few different ways that we can test for multivariate normality. We also, there is an assumption of linearity because we're looking at R squared and R. And so linearity among pairs of variables is assessed through, scatter plots, the kind of normal basic ways that we look at whether or not two relationships appear to be linear. And then finally, outliers. If we have extreme outliers, whether those be multivariate outliers determined through something like Mahalanobis distance, or individual outliers on a specific outcome, we can find those through, box plots or the like. And so our data does need to be screened in general for problems like that. But for the most part, the assumptions that we have for regression are not quite as strict when we're talking about factor analysis. All right. I already talked a little bit about this, but when it comes to factor extraction, principal components assumes that the diagonal is 1, while factor analysis assumes that the diagonal is composed of some sort of shared variance. Orthogonal rotation, I don't know why I've got all this again. Orthogonal rotation means that our variables or our factors are completely uncorrelated. Oblique rotation means that our factors are correlated. And after we do a factor analysis, we can request factor scores. And you can use these factor scores as either predictors in a model or kind of any other thing. So you might have a very high factor score on one factor and a very low factor score on another factor. And it is basically each individual's mean level of a given trait. All right, extraction. So here we have two different types of rotation. When I was drawing my lines, I was like, okay, so we have factor 1 here and we have factor 2 here. And in this example, we have all of these responses, all of these items, right, that are clustered around this factor but not quite there. And rotation allows us to put a closer line on where these things might be relative to this factor, right? And you notice that when you rotate this factor this much, you also rotate this factor this much. And as long as these are orthogonal, you should see a consistent change in these factors. Now, when you do this, the factor scores of these will become stronger relative to this factor and weaker relative to this factor. Notice that this factor is getting further away from these items as we move this way, and this factor is getting closer. Well, this isn't a great line. It might actually have been better to go right through here, but it's getting closer as we move closer to those factors. In contrast, if our factors were like this, you can see that these factors are correlated. No longer is there a 90-degree difference between factors, right? In fact, these factors are getting closer together. And so these don't rotate together, they rotate differentially. They rotate to make the best fit with the items consistent with this factor. Oblique rotation often does give you a better fitting model, but unfortunately it also means that it's more excuse me, subject to scrutiny, because if you have just like, imagine that there was a big pool of data right here as well, and you plotted another factor through here. Well, it could be that you have 3 factors. It could be that you only have 2 factors, and some of these should be here and some should be here. It could be that you have multiple factors, or it could be that there are no real factors, and all of this is just being driven by chance. So that is it. I look forward to seeing you guys this week, and we will put some of this stuff to the test.